Hola a todos, buenos días. Pues muchas gracias por asistir a esta sesión del seminario. Es un placer presentar al profesor Xiang Yang. Él nos visita de la Universidad Shanghai Jiaotong. El profesor Chang es profesor distinguido pues, de esta universidad. Esta universidad es una universidad muy prestigiosa, entonces estamos muy complacidos de tenerlo aquí. So, hello everyone, welcome to this session of our seminar. Uh, I am honored to introduce Professor Xiang Yang. Professor Chang is a distinguished professor at Shanghai Jiaotong University. Professor Chang is a very distinguished professor there. He has made a lot of contributions in dynamical systems and differential equations. So Professor Chang, thank you for being here. And he will talk about global dynamics of a classical predator-prey model with sigmoid functional response in slow, fast setting. So thank you.
Okay, thank you. Many thanks for your attendance. This is my second talk. The first talk is mainly on the integrability. So this talk is about the dynamics of a concrete model. Yes, this talk we talk about this model. This is a classical predator-prey model. You see, this is the logistic style. This F is a functional response. If you to study the dynamics of predator-prey model, this is a very popular model. Since for this model, there are, or similar this model, there are a lot of studies, and also a lot of results. But usually, these functional responses usually use the Horning type. This Horning type has totally 4 types. The first 3 given by Horning, the type 4 given by the Andrew. This is the linear one. This is the fractional linear. This is the extension from power 1 to power n. Yeah, this is a classical Horning type 3. This is the power 2. This Horning type 3 has a generalization, has this linear part. So in this talk, the dynamics of the system has this form. This is called the sigmoid functional response. Sigmoid means the function has something like this way. Just as I said, this Horning type 4 is given by Andrew. So for unified, so this functional response also add to the Horning types. This is called the Horning type 4 functional responses. Here is a reference. Related to this model has this Horning type functional response. There are a lot of results for studying the global stability limit cycle. Limit cycle means the periodic orbit, isolated periodic orbit. Heteroclitic or homokinetic bifurcation. Homokinetic bifurcation means that these 2 equilibrium collect these 2 heteroclitic orbits. Maybe they can form a heteroclitic. This is the heteroclitic orbit from this equilibrium to this equilibrium. Then there is another orbit go back from this equilibrium, go back to this. This forms a homokinetic loop. So also study the bifurcation from this homokinetic loop can be bifurcated some limit cycle or not. And also homokinetic means that the orbits positively or negatively go back to the same equilibrium. It's called the heteroclitic orbit. Also study the Bogdanov-Tax bifurcation. This is very special in dynamic system. I don't want to explain. A lot of publications here. You see, I list according to years, list some of them here. But even though very few cases, the dynamic completely solved. Even published a lot of publications here, but very few system is dynamics can be completely characterized. very few. So now we focused on the pre-model 1 with these sigmoid functional responses. And later on, I will say, tell you what results are known for these models. So now we must say here, in my title, I say the model in through-fast setting. Maybe here some people working in dynamic system study the Hopf bifurcation. If we study the Hopf bifurcation, we compute the first and second Lyapunov constant. Then after the bifurcation, we can get 1 or 2 limit cycle. We only say we can get some limit cycle from a Hopf bifurcation, but we cannot say anymore. If we use the singular perturbation theory, then we can get more interesting result from the Hopf bifurcation. So singular perturbation theory is a very strong tool to study dynamic system. So now we recall the system. This is the system. These are the functional responses. You see, this system has 1, 2, 3, 4, 5, 6, 7. Has 7 parameters. See, a system has too many parameters. If we want to study global dynamics, usually it's not easy. So we try to simplify the system such that the system is equivalent to a simple form. So after rescaling, only rescaling on the variable x, y, and the time, then the system can be simplified to this case, to this form. So now I write here. Is x dot equal to x 1 minus x minus f of x, y is y dot equal to y minus mu plus beta f of x. Is f also in this simple form is x squared over x squared plus c1x plus c0. So now this system has only 4 parameters, mu, beta, c1, c0. The system has a little parameter, then the start to become a little easier. So for our next study, all the results depend on this system. Since this system, only after rescaling, this system can be transformed into this system. Now we record a long result on this system. For C1, negative, C0 positive, but this denominator does not equal to 0, does not vanish. Then here there is a result given by the 2008 in Journal of Dynamic System and Differential Equation. It's by the Christian Ruth from the Caltech Tibet University, with her co-author. Complete give the classification depend on these parameters. You say it's study the Bogdanov tax bifurcation of Q-dimension 2 and 3, and also the Hopf bifurcation of Q-dimension 1 and 2. They are studied only the locally have some dynamics, but they do not have method to get the global dynamic. So later on, we will use our tools to extend this result from locally to globally. This is one of, for C1, C2, both positive. This is both positive, and the denominator does not vanish. Then this is Huang from the Alabama University of United States, and his co-author in 2020, he proved that in these cases, if the equilibrium, since we start, this is this x is a prey, y is a predator. So we only start in the first quadrant. This is the x, this is the y. We only interested in dynamics in this region. So they proved in this case, in this paper, they proved that if the one equilibrium here is locally stable means that the eigenvalues, the two eigenvalues, has a negative real part. Then they prove that this equilibrium is globally stable. Means that from any orbit from any initial point, then they finally go to this equilibrium. It's called globally stable. Then in 2020, in 2021, my colleague with me to prove that if the equilibrium here is unstable, then we prove that this thing has a limit cycle. If locally stable is globally stable, proved by Professor Wenzhang Huang. If this equilibrium is unstable, we prove that this system has a periodic orbit. And also in the surface setting, we can get a more interesting result. This is a long result for this system with C1 negative, C0 positive, and this denominator does not vanish. Second one is C1 positive, C0 positive. This denominator does not vanish. Then we have this long result. This is for local bifurcation. This is for global stability. This is for the existence of limit cycle. Yes, if this denominator has zeros, if this denominator has the zeros, in 2000, this is from Wuhan University. It's from Wuhan University, China. If they prove that under condition, if this fx, this denominator, has two different real roots, they prove that also have some additional conditions that prove that if the equilibrium is locally stable, then it is globally stable. This is a long result about this system with this functional response. Now, so we want to study all the possible dynamics for this system with the parameter. So according to previous study, we studied three cases. The first one this fx can be written in x squared over has one double root. Second one is the fx can be written in x squared. X has two different roots. The third one is the fx equal to x squared, but here we write in another form, different from here, use alpha squared f plus beta x plus 1. This form is exactly given by in this paper. We write in this form exactly according to this paper. So now we started this dynamic of the system with functional responses. We consider these three cases. The first one has the denominator has a double root. Second one has two different roots. The third one has no root. We studied according to these three different cases, study the dynamics of this system. Yes, first one we consider these cases. Yes, we will start here there is a positive equilibrium. We will prove that if the equilibrium is locally stable, then we prove that it is globally stable. We will use the Dirac function and also some other tools. Second one, if this equilibrium is a weak focus means that the eigenvalues has a pair of pure imaginary eigenvalues. Then we prove that this is weak focus is is of order 1. Maybe if people work in qualitative theory, maybe say, this is easy work to compute the Lyapunov constant, but no. Since the for concrete system has a lot of parameters, this equilibrium has an expression very complicated depending on these parameters. Then if you compute the first Lyapunov constant, then the expression becomes very, if you use maybe several pages, you don't know is the Lyapunov constant is positive, vanish, or negative or not. But we use some special tools to distinguish this order. This is order of the weak focus. Then we prove that if the equilibrium is unstable, we prove that existence of the limit cycle. Then this is I think is the last result. From the Bengala-Dirac theorem, we can get the limit cycle existence. Use the Hopf bifurcation, we also can get the limit cycle. We only say after under the bifurcation, Hopf bifurcation, we can get one limit cycle. We cannot say anymore. But if in the surface setting, we use the geometric singular perturbation theory, we can say more about the deformation of the shape of the limit cycle. This is, I think, the singular perturbation theory is a very nice tool. Yeah, this is the Dirac function. We can see this given by the Professor Yanqian Ye is a theory of limit cycle. This is a very famous book in the qualitative theory. Yeah, this is, I say, proves the global stability use of some special tools is from this paper. Yes, compute the Lyapunov constant. There are many references. I only list one of them. To study the shape of the limit cycle, here we will introduce what is the Gallard explosion or relaxation oscillation we will introduce. You can see these two books, the two papers given by Krupa and Zimoni, published in 2001, these two papers. These two is the last papers to study the dynamics of the surface system. This paper, yes, for this case, the paper published in 2020 in the SM Journal of Applied Math. Next is the main result. This system in this case has at most two equilibrium. And also for some special parameters, the two equilibrium can happen. If the two equilibrium appear, A must belong to 0 and 1. So here is x equal to 1.
You are working for the second case, okay?
The first case is
Okay.
the first case. This is A. So in order the system has two positive equilibrium, must be A belong to 0 to 1. In these cases, yes, A is here. In this case, if the system has two equilibrium, then one is locally stable. Locally stable means global stable. I will show you what is the global stable. Another one is a saddle. We can get the global dynamics. Is a phase portrait. Since the x equal to A here is locally stable, then we can prove that this global stable in this region. Global stable. Here is the saddle. Saddle has a global dynamics. This is the Bengala disk. This is a Bengala disk. This is a saddle. We have the global dynamics. This is a global stable. This saddle is a stable separatrix. Negative is here. Negative is at the infinity. This is the unstable. separatrix go to infinity. This unstable separatrix go to this point. This is this point. This is a global dynamics. This proof, if you familiar with the quality theory, this proof is not difficult. It's easy proof. Second one has a unique equilibrium. This is more interesting. When the positive equilibrium is unique, then if it is stable, it is globally stable.
It's stable locally, you mean?
It is stable means locally. If the eigenvalue has two negative eigenvalue and negative real part, then it is globally stable. Yeah. If it is a weak focus, then it is off order one and stable.
Sorry, what do you mean by weak focus?
Weak focus means that for this system has a, for example, for x dot equal to f, x, y dot equal to g, x, y, an equilibrium, x 0, y 0. Equilibrium means that this f, g, both equal to 0. Then we compute the eigenvalues of this system related to this this equilibrium. We compute the Jacobian. X 0, y 0. Compute the eigenvalues of this Jacobian. The Jacobian may be lambda 1 equal to alpha plus I beta. Lambda 2 equal to alpha minus I beta. The weak focus means that this alpha equal to 0, beta not equal to 0. In this alpha equal to 0, beta not equal to 0. So in this case, we call this equilibrium is a weak focus. To know, then we compute the Lyapunov constant. We know this is a weak focus of order 1 is also stable. If this unique equilibrium is unstable, then we can prove that the system has a limit cycle, a unique limit cycle. This limit cycle in the three-phase setting. Three-phase setting means that later on we will write this system in this way. Move with mu after mu y minus 1 plus gamma f of x. Later on we write this system in this way. Since later on we will see many interesting things depend on this beta over mu. The ratio is important. Not only mu and beta, but this ratio is an important quantity. So we move this mu after. Then if this mu is small, is mu natural 0. If this mu is small, then this system called the three-phase system. So I say in three-phase framework means that we write the system. This second equation is this form. This mu is a very small parameter. Then this limit cycle, I say, from Hopf bifurcation, we can get a limit cycle. We say get a limit cycle. We cannot say anymore. But in the three-phase setting, we can say more interesting things. We can say this small limit cycle can expand. How to expand? Then expand to a relaxation oscillation. Maybe this is more interesting from physics. A relaxation oscillation. But from the small, see the Hopf bifurcation limit cycle is very small. Relaxation oscillation is a big one. From small to big, but the limit cycle from small to big is passed from a series Gauss limit cycle. This Gauss is from French. is dark. Is dark. Color explosion. We will explain what is the color explosion. Later I will explain. Yeah, this is main result for system has this functional response. I say the first case. This is easy to prove. If you work in qualitative theory, is not difficult. Yeah, but this is I say this is to compute the big forks of order one. Theoretically only a calculation, but this is not an easy calculation. Very complicated. There are some techniques. Forget the existence of limit cycle is not difficult, but we can use this geometric singular perturbation theory. We can get half the Hopf bifurcation, the limit cycle, obtained from the Hopf bifurcation. The limit cycle have to the shape have to change it. This is the interesting. Yes, now we say here we have the Gaussian explosion. What is the Gaussian explosion? Gaussian explosion means that the system Gaussian explosion is a dynamic phenomenon for self-fast system. It is only for self-fast system. With two parameters. One is the perturbation parameters. Here, for our case, mu is the perturbation parameters. We have another parameter called the breaking. Breaking, like this parameter, if you change a little, the dynamics completely different. This is called the breaker. Here, for our case, the breaking parameter is mu, is gamma. If we fix this perturbation parameter very small, then we change this breaking parameter. Then we have a singular Hopf bifurcation. If you work at quality theory, everybody knows what is the singular Hopf bifurcation. This Hopf bifurcation produces a small limit cycle. Then the small limit cycle becomes a Gaussian cycle without. Later, I will have the picture shows what is the Gaussian cycle without the head. Then to the Gaussian cycle without the head enlarge becomes a here is a mistake. Becomes a transitory cycle. Becomes a Gaussian cycle with head. Finally, to relaxation oscillation, you can see this picture. Yes. In our cases, this red curve is an important curve in the dynamics. These curves corresponding to this equal to 0. In our cases,
Sorry. This you have the tracking parameter
Yeah.
which is changing, and you have this behavior as changing the parameter.
yes,
Okay.
yes. This red curve here is this one divided by x. This given by this function. This red curve. This is very important. Okay. Now, if the equilibrium is here, then this point is called the colored point. Later we will explain what is the colored point. If the equilibrium is here for epsilon equal to 0, for mu, in our case, for mu equal to 0, the equilibrium is here, then we mu change it very small, a little. Here, we will have a Hopf bifurcation from here. Hopf bifurcation produce a small limit cycle. This every people knows from the qualitative theory. Is a small limit cycle. Now we change the gamma a little. Then this limit cycle has this side with distance only capital O. Is O mu. See, the mu is small, this is small. So this Hopf bifurcated limit cycle with this for some special value, the gamma. Gamma is just, I said, called breaking parameter. Now gamma changed a little, appear the Hopper bifurcation. Then we continue to change. Then these two sides come close to this red line, red curve. With gamma changed very, very small, this cycle called the Gardner cycle without the head. Then we change the gamma a little to here, this become big Gardner cycle without the head. This is called the transitory cycle. Transitory cycle. Here, then change the gamma continuously, then become this. Called Gardner cycle. This is like a Gardner duck. But here you cannot see the duck, but here seems like a duck. Quack, quack, duck. This like. So this is called the Gardner cycle. Then to continue to change the gamma, this becomes relaxation, oscillation. But from here to here, why call it Gardner explosion? Why? From here, no, from here, change a little such that this cycle becomes a Gardner cycle. From here to here, the parameter lambda, this parameter gamma changed. For example, here, there are some values of gamma 0, then gamma change from gamma 0 from here to here. Gamma changed only K is a positive constant. Since the mu is very, very small, then it's exponential function. This is minus. Exponential function becomes really, really small. So gamma changes from gamma 0 only in e power minus k over mu. Mu is a very small parameter. So it's so small. Then the Gardner side from here, the shape from here becomes here. This is called the Gardner explosion. The gamma becomes changed only from gamma 0, only these small values, the shape of the limit cycle changes shape from here to here. So fast. It's called the explosion. So this cycle is called the Gardner cycle. This is called the Gardner explosion. Yes. Here is a simulation. We take A equal to, this is not these things. I say A belongs to 0 to 1. In this case, system has two equilibrium. Now our case is this theorem here. We have only one equilibrium. Only one equilibrium. Now A is a negative. We choose A equal to these values. Then we take the simulation. You see, this is the gamma. Gamma 1. Gamma 1 means that the equilibrium is here, and the beginning is here. Gamma 2. Later we have a gamma 2 means that the equilibrium moved to here. When gamma take equal to gamma 1, the equilibrium is here. When gamma take gamma 2, the equilibrium is here. Now we take a gamma changed from, you see, this is a Gardner cycle. This is the initial point. Then to here, this is the limit cycle. This is the Gardner cycle without the head. This is the same initial point. This is take the simulation. This is the Gardner cycle with big head. This is the periodic orbit. You see, from this Gardner cycle without the head to this Gardner cycle with head, the parameters change only from 7 to 8. The parameter changes only a little, but this shape of a limit cycle changes from here to here. This is called the Gardner explosion. Then we change from here, we change the gamma. Then the equilibrium from here to here. This is the relaxation oscillation. This is. One time I taught my student from ordinary differential equation, I ask my student to simulate the Van-Boer equation. This is a famous equation, Van-Boer equation. I say, inside there is a very interesting dynamics. You can try to simulate. Then the next course student come here. We can only simulate this relaxation oscillation. We cannot get other interesting dynamics. You see, this parameter only from here to here you can get. Otherwise, it's not possible to get. So if you do not have a theoretic theory support, you cannot get this one. See the parameter it's very difficult to choose this small gamma. Usually, student can simulate this relaxation since when gamma changed such that the equilibrium move from here to here, the system has relaxation oscillation. Then when gamma deal to here, then the relaxation oscillation shrink. You see, when gamma deal to gamma 2, this relaxation oscillation shrinks to this with the big head, then only this limit cycle, this color cycle, then it disappear. When gamma moved from here, gamma increased such that gamma increase or decrease. From here to here, the equilibrium move from here to here, then the relaxation oscillation then shrinks to the origin, shrink to this colored point. So we give the theorem and give the simulation. The proof, I don't want to say this one. Yeah, the proof use the singular perturbation theory. Just like I said, we write the system in this way. This system after time change, time rescaling, this system becomes this next one. After this time change, the mu appeared here. This is called the slow system. This is called the fast system. Because this mu is small, so this time is small time. This is slow. This is small. This is big. So this is called the fast system. Is called the slow system because of this time. Yes. Oh, okay. Even for this two-dimensional system, I say for this model, the known results, very few known results, because we do not have very good tools. We use a single perturbation. We can use these good tools to get more interesting results. You see, now this system we limit mu equal to 0, this equal to 0. Here, if you take mu equal to 0, this becomes a 0. So for the fast system, we take mu equal to 0, this is 0. This slow system, we take mu equal to 0, this is 0. So this is a two-dimensional system. In fact, this is a one-dimensional system. This is a functional equation, is a differential equation. It's a one-dimensional. One-dimensional equation, the dynamics is very clear. If we only compute the equilibrium, then everything will look very well. This is a two-dimensional, in fact, this is the one dimension. Since y dot equals 0, so y equal to constant is the first integral. So for this system, for this system, every line y equal to constant. This is a solution. This is invariant. So the y equal to constant is the first integral. So this, in fact, this is also, so this is called a layer system. Layer system means that the dynamics on each layer. But this is one dimensional. On each layer, the system is one dimensional. The dynamic is very easy. I said this is also easy. From this equation, we solve the y equal to 5x. Another one, we solve the equation, for example, y equal to 5x. We we solve this equation, get y equal to phi x, substitute to this equation, becomes phi dot equal to phi of x minus 1 plus gamma f of x. So this is also one-dimensional. These two one-dimensional dynamics very clear, also very simple. So now the singular perturbation theorem gives a nice tools to combine the dynamics of these two systems, get a global dynamics of the original system with mu small. Yes, now this is the M0, is this equal to 0? This is the S shape. This is not S shape, depend on parameters. So we call it S0. S0 is this one. But we said here is better to say here we write in X. Now we write S in C of X, Y. No. Is C of X minus Y. Maybe is 1 over 6. 1 over fx. No. Yes. Here is 1 over f of x. Here is y minus 6. This is S0. This is called critical curve. This is here is S0 and also has x equal to 0. This curve we do not interest in this one. We only interested in this S0. You solved from this equation. This is called critical curve. This critical curve is really important in the study of dynamics of this system. So we substitute this C of x into this equation, we get this equation. Now we say a little more about this system. What is the Gauss explosion? Now, this S0 has 3 different shapes. One is strictly degrees. Another one is degrees, but with one critical point. Another one is S shape. Just I should. This is the S shape. This S0 has 3 different shapes. This is strictly degrees. This is degrees, but with only one critical point. This is S shape. This S0 has these 3 different shapes. Now, when we restrict this system to this curve, the dynamics given by this one. You see, if the derivative of c with respect to x equal to 0, then this equation is a singular equation. Since if this has, for example, here, at this point, the derivative of c with respect to x is 0. Here is 0. Here is the 0. It vanished. Is the derivative here. So later we will define the another notion called it normally hyperbolic. Normally hyperbolic. Another one is called the jump point. Another one is called the Gallard point. Three notions. Normally hyperbolic. Now, Yes. For this equation, for this equation, if we compute, we dilute this one by p x y, or this function diluted by p of x y. Now, you see, on this curve, p equal to 0. Yes, this is our definition. On this curve, so this curve defined by this one. This is only this equation move out x. So here, for this, we compute the derivative partial p with respect to x. Then, in these cases, all the derivative along this curve does not equal to 0. This derivative with respect to x, so this is the normal direction of this curve. For here, this is the derivative. Here is equal to 0. Here is equal to 0. All the other points, this derivative, partial derivative, does not equal to 0. So all these points is normally hyperbolic, but these 2 points not normally hyperbolic. At these 2 points, the partial derivative equal to 0. Okay. Now, so this is what is normally hyperbolic. What is jump point? What is the Gallard point? Jump point, if the dynamics, maybe it's better I write here. For this one-dimensional system, if on this one-dimensional, if the dynamic is this way, this is the jump point. For here, if this go up, so this is the Gallard point. This is the jump point. Jump point. Why jump? You see, and here the dynamics is this is I go back. Yes. For this system, the dynamics is one-dimensional on each line. This is dynamics like this one. Very easy. So you see, this is normally hyperbolic. So any initial point from here, the orbit come to here, then go down from here, then jump. This is called the jump. But if in these cases, if, for example, you start from here, then shrink to this curve, then nearby go up to here, then have several possibilities. One is the possibility is jump. One is the possibility from here. Have 2 possibilities. Of course, if this orbit come here, go back, then this is the Gallard solution. But here, the only orbit must jump away. So it has 3 rotations, normally hyperbolic, jump point, and Gallard point. Depend on jump point and Gallard point in this book, in these 2 papers, has very detailed theory to state what is dynamics near this jump point and the Gallard point. They state very clearly here. Yes, what is the time? Oh, the other one. Oh, sorry. Okay. Now, for different values of A, they can have this strictly decrease. In these values, this critical curve is decreased but has 1 critical point. For this is S belongs to this interval. The curve has this S shape, and yes, an S shape. Yeah. For these three different cases, we depend on these three different cases. We study the dynamics. Then the tools is here. I say, and in case has unique positive equilibrium, we prove the global stability. We use the Dirac function and also use one tools. Tools I will explain what is the tools to compute the diaphragm constant. Then start the Gaussian explosion. Gaussian explosion depends on this series given by Krupa and Zimoni. Yeah. Yeah, this is I say how to start the global stability. This is the tool here. I only if you are interested, you can read my book, my paper published in 2022. Yes. Yeah, these are another cases. Yes, maybe we do not have enough time. I explain too much here. Then it has two different rules. Then since according to the symmetry, we can only distinguish B larger than L larger than 0, or in this case, or this only these three cases. This case, the paper published in Study in Applied Math in 2024. Here we depend. Here they do not have interesting dynamic. This is only the global stable. This is a global stable, and this is this dynamic is similar to the previous case. In this case, do not have interesting dynamics. Interesting case is this one. In these cases, this case here, for some values here only one equilibrium. This equilibrium is a saddle. With the change of parameter, the system has a new equilibrium. This equilibrium is here is stable. This equilibrium appears a new equilibrium. And why is it interesting? This is saddle. If this point stay this point, then here is a colored point. Then the system can have a subcritical Hopf bifurcation can produce an unstable limit cycle. Here, if these two equilibrium meet together, if two equilibrium coincide, here or here, this only has a saddle bifurcation. If these two equilibrium coincide here, then the system has Bogdanov-Tax bifurcation of two-dimension 2. So this is a very interesting cases. For this A less than 0, less than B, with different for this ratio has different values. This if it has these two cases, if the system has these two equilibrium, the system can have Bogdanov-Tax bifurcation if they coincide here. If coincide this side or this side, only saddle bifurcation. This is simple. If saddle is here, this point move to this point, then this becomes a guarded point. Then can have the Hopf bifurcation, can produce a limit cycle. This limit cycle can have a limit cycle. This limit cycle increased, then becomes a homokinetic loop. Becomes a homokinetic loop. This here we use the singular perturbation theory. We can prove strictly the limit cycle can expand to this homokinetic loop. Then the homokinetic loop destroyed. Then they have the stable circuits have three different cases. But in quality theory, usually it's difficult to distinguish this stable characteristics. The negative could be this point or this point or this point. It's really difficult to distinguish. But in three-phase setting, we can say there exists some parameters such that these cases happen, or we can prove there are some other parameters such that this case happens, and also this case. These three cases all can happen. we use a singular perturbation theory. We can prove. So this is so I say singular perturbation theory is a very powerful tool. So in this paper, we get a new dynamic phenomena. We said the subcritical homomorphication can produce an unstable limit cycle. This unstable limit cycle can undergo gather explosion to homocritical loop. Before never has this result. We only say the here has a homomorphication produce a gather cycle, then becomes a relaxation oscillation like this way, but we do not previous never have results say this cycle can explode into a homocritical loop, then disappeared. This is a new phenomenon we found in this paper. Yes. The last one is these cases. In fact, this case denominator do not have the real root. This is really a difficult problem. I work with my students more than 1.5 years. Then we in fact do not completely finish. Also remain a little things inside. We don't know how to solve. This is really a difficult problem. Since I said this case started by Christian Russo from Tibetan University. They get the locally bifurcation of the Bogdanov text bifurcation of codimension 2 and 3, and also Hopf bifurcation of codimension 1 and 2. They only get the local bifurcation. We want to know how to use this local bifurcation get global dynamics. This is our main aim in this paper. This work is is just published in Journal of Differential Equation. Now we use just I say the critical curve has these 3 shapes. Now we can use this shape to distinguish the bifurcation. Yes. Yeah. Yes. If the critical curve is strictly degrees, do not have interest in bifurcation. If here has one these degrees but have one critical point, then here has some interest in bifurcation. In these cases, here can have the yes. We could here, yes. Just as if this curve is strictly decreased, then have if the equilibrium located at this critical point, then have the Hopf bifurcation of codimension 1. If the two equilibrium coincide, some other, for example, here or here, is only satellite bifurcation. If these two equilibrium coincide at this point, then become the Bogdanov text bifurcation of codimension 3. We use this geometry to distinguish what is the bifurcation. Then, yeah. Yes, here now we only start this S shape. Yes, if two equilibrium coincide here or coincide here, then these 2 points, these two equilibrium is a Bogdanov text bifurcation of codimension 2. If the equilibrium not degenerate, equilibrium only one equilibrium stay here. Here can in these cases it can be Hopf bifurcation of dimension 1. In these cases, this point can be Hopf bifurcation of codimension 1 or codimension 2. Two different cases. If the equilibrium is here, only non-degenerate. It here can only have Hopf bifurcation of codimension 1, but here it's possible Hopf bifurcation codimension 1 or codimension 2. Then we use this Hopf bifurcation, we get the limit cycles. get the global dynamics. But now that one is very complicated. I don't want to say more about this one. This is at least the theorem here. A lot of cases to state. Yeah. Instead here, a lot of result here. I don't want to explain more detailed. If you are interested, we can talk about this a little more. Okay, thanks. Okay, thanks.
So thank you, Professor. Do you have questions or comments?
Thanks. In the case of you have a generalized Hopf bifurcation, you can have two limit cycles. My question is if you can have a double canard. Is it possible?
What do you mean double color?
I don't know, maybe a small head and a big head canard.
Yes. Here we do not have. In fact, yeah, this is a very interesting question. Why I say this is an interesting question. Double galat maybe is like this is a double galat. But this is double galat until now. Recently there is one paper, but I don't know this paper is correct or not. You do not have the last theory to study this kind of double galat.
Okay, let me ask you, in the case of the codimension 3 Bogdan-Optakis bifurcation, have you exploited all the richness of this?
Sorry?
Have you exploited the, have you taken advantage of the codimension 3 bifurcation, a lot of codimension 2 sub-bifurcations?
But here, I think you can see from here. As you know, Bogdanov target bifurcation of dimension 2, the theory is completely. But Bogdanov target bifurcation of two-dimension 3, the theory is not complete. Have some result published by Dumartier, is Rulatic, I think, published in Agodic theory of dynamic system some years ago, but this is not a complete classification. Until now.
Finally, can you give the reference of 2025 that you mentioned on GDE, Journal of what's the reference of your last paper? That one?
Yeah, this
what's
is
the title? Do you have it? The title of this paper?
But if you check the mass signet, use
okay.
Sue and my name, you can find it. Yeah,
Thank you.
You can see this your problem here. Yeah. No. Yeah, this is the PT3. You change the parameter a little, then we studied these cases. All these possible can happen bifurcate from these cases. From here, this is the PT3. From here, how to bifurcate from this very degenerate cases. Then we start this to here. Sorry. From here to all these cases, this is the bifurcation. But I said this is do not completely classified. Remain some small thing inside. We don't know how to solve it. Really difficult.
Thank you.
Thank you. Do you have more questions or comments? No? Okay, well, if not, we thank again Professor Zhang.
Okay, thanks.
Thank you very much. So, yeah, thank you very much for being here. Muchas gracias por acompañarnos en estas pláticas. Muchas gracias.
Gracias, muchas gracias. In fact, I stay in Barcelona for 3 years, but I can speak a little Chinese Spanish.